Many times you're asked to determine the pH of a particular solution. And the way I see this, there are 5 different types of solutions that you're going to be facing when you do this. And if you can categorize the solution that you have as one of these 5 types, then it helps you to know what you have to do to determine the pH of the solution. The 5 different types of solutions are strong acid, strong base, weak acid, weak base, and buffer. What we're going to do is we're going to go through each type of solution, give you some pointers as to how to identify it, and then also how to solve the problem of determining the solution pH. So let's begin with strong acid. There are very few compounds that fit this bill, but strong acids are compounds that completely dissociate in water to give hydronium ion and their conjugate base. Or at least we assume complete dissociation. So a typical model for this would be something like this. We have a compound in solution, it combines with water to make hydronium ion and the conjugate base of the strong acid. Now note that the conjugate base of the strong acid is of negligible base strength, which is something we'll talk about later on. Technically this, even though we write it as a chemical equation where all products form, it still is in equilibrium. It's just that the equilibrium constant for this dissociation is so large that we assume that complete dissociation occurs and formation of products happen. Now, there are 7 compounds that are considered to be strong acids, and we list these below. And the best thing for you to do is just to memorize these compounds. The most common ones on this list are hydrochloric acid, nitric acid, and sulfuric acid, because those are acids that are commonly used in laboratories. But it's worthwhile to remember the other ones as well. Now, how do we determine the pH of a strong acid solution? If this is true, essentially what we can say in all cases but one is that the hydronium ion concentration is equal to the molarity of the acid that's given. The one exception to this would be sulfuric acid, which is a diprotic acid. Sometimes it's best to assume that with sulfuric acid both protons come off so that the molarity of the hydronium ion would simply be twice the molarity of the acid. However, the second dissociation of sulfuric acid does not occur completely. There is an equilibrium involved with it, which lies heavily on the right, but not completely. So if you want to be really precise in your calculations, you have to account for that, though most times there's no need to do that. So you just assume that the concentration of hydronium ion is simply twice the molarity of the acid. To get the pH, you simply take the negative log of the hydronium ion concentration then. Let's move on now to strong bases, which are just about as easy, but there's one thing that people sometimes forget with these. I consider a strong base to be a hydroxide salt that is highly soluble in water. Something like sodium hydroxide, where if you take the hydroxide salt as a solid and dissolve it in water, it does dissolve and it dissociates. Now, there are only 2 types that do this. You have monocation hydroxide, such as sodium hydroxide, and then you have dications like calcium, barium, and strontium hydroxides, which will also dissolve in water. In both cases, it's assumed they completely dissociate. You form a strong electrolyte solution, and it's easy to calculate the hydroxide ion concentration based on the molarity of the base. There are 9 compounds that are considered like this, and they're listed below. Now you can also figure these out from the solubility rules. The one that is difficult to see from solubility rules is thallium-1 hydroxide, because some solubility rules don't list that one, but it is considered a strong base. Now, how do we treat these? Again, if you have something like sodium hydroxide, the hydroxide ion concentration would simply be tied directly to the molarity of the base. In the case of something like calcium hydroxide, then you have to remember that the hydroxide ion concentration will be double the molarity of the base. To do this, we would calculate the pOH, because we actually have the hydroxide ion concentration, so we would take the negative log of the hydroxide ion concentration, and then to get the pH of the solution, we would subtract that pOH from 14. Okay, let's move on to weak acids. Weak acids are any compounds that do generate protons or hydronium ions in solution, but do not completely dissociate. So if you have a compound that is considered an acid, but it is not one of the 7 strong acids that we listed earlier, it's safe to assume that that compound is a weak acid. And what happens is we set up a true equilibrium. We have the weak acid in solution in equilibrium with hydronium ion and its conjugate base. And so we would write a mass action expression for that, which we designate as Ka. And a typical Ka expression is simply the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the conjugate acid. Now, how do we solve for the hydronium ion concentration in a weak acid solution? Let's set up the equilibrium again, and we'll set up an ice table. Now, initially, what we're going to say is that we have a solution that is all the associated acid. So we would substitute the molarity of our conjugate acid in as the initial molarity of the acid. We will say, for the sake of simplicity, that the hydronium ion concentration in this solution is 0 molar, although technically that's not true if we're dealing with an aqueous solution at 25 degrees centigrade, since there is a little bit of hydronium ion from the autoionization of water, and the concentration of the conjugate base is 0 molar. Now what's going to happen? We're going to have a shift to the right, so we're going to form some hydronium ion and some conjugate base, and those increases in molarities will be equal, and the decrease in the molarity of the conjugate acid is the same, since it's a 1-to-1-to-1 equilibrium. So that means at equilibrium, the concentration of the conjugate acid is going to be the original concentration minus X, and the concentrations of both hydronium ion and the conjugate base are going to be X molar. So we can plug those into our Ka expression. We would need to have a numerical value for the Ka to solve this, and we get something that looks like this. Now, in many cases, what we can also do is make an approximation, because if we're going to solve this one precisely, we would use a quadratic formula to do it, and it will always work to do this. But if you have a fairly small Ka with respect to the initial concentration of the conjugate acid, what you can often do is say that the value of X is going to be very, very small with respect to that initial concentration. So what we can say is if X is significantly less than the initial concentration of the conjugate acid, then the difference between the two is approximately going to be equal to the original concentration of the conjugate acid. There are different opinions about the guidelines that you can follow for this, and what I would recommend is that you consult your instructor or your textbook for those guidelines and use whatever guidelines you're told there. And this keeps you out of trouble in terms of the calculations. If this approximation can be made, then what we get is this. And if we solve for X, we can just take the square root of the Ka value times the initial concentration of the conjugate acid. Since that X value equals the hydronium ion concentration, then that would give us the hydronium ion concentration. And once again, we can solve the pH by taking the negative log of that hydronium ion concentration. Now, weak bases are similar, except that a lot of people forget that there are really 2 types of solutions that can give you weak bases. One is simply a solution of a compound like ammonia, which will act as a weak base by itself. But the other is if you have the sodium or potassium salt, which are the most common ones, of the conjugate base of a weak acid, that solution will also act as a weak base. In both cases, what happens is the weak base hydrolyzes, meaning it combines with water, it pulls a proton off water, and forms a small amount of hydroxide ion in solution. Now we can write a Kb expression for this. The Kb expression would simply be the concentration of the conjugate acid times the concentration of hydroxide ion divided by the concentration of the conjugate base. The way I've written it here is I'm assuming that the conjugate base has no charge, which means the conjugate acid would have a positive charge. If you're talking about the conjugate base of a weak acid, such as fluoride ion, for example, then your conjugate base would have a negative charge, and the conjugate acid would have no charge. But the equilibrium is the same, and the Kb expression is the same. Now, how do you determine a Kb value? Again, you can look some of them up directly from tables, but if you have the conjugate base of a weak acid in solution involved in this equilibrium, then what you have to do is you have to calculate the Kb value by dividing Kw, 1.0 times 10 to the negative 14th, by Ka. We can set up the same kind of problem that we did before with the weak acid. We start with a concentration of our weak base in solution, and we assume that the concentration of the conjugate acid is 0. And also, again, for the sake of simplicity, we will say that the concentration of hydroxide ion in this solution is 0 molar, although technically it's 1 times 10 to the negative 7th molar if we're dealing with water at 25 degrees centigrade. So once again, the conjugate base will hydrolyze, and for the sake of difference, I use the variable y instead of x because we're solving for something different. So we're going to form some conjugate acid and some hydroxide ion from this hydrolysis equilibrium, and we're going to lose some of the conjugate base. The result is that we have conjugate base. The conjugate base molarity is the original molarity minus whatever has hydrolyzed. Conjugate acid molarity is Y, and the conjugate hydroxide ion concentration is also Y molar. If we plug those into our Kb expression, we get something that looks almost exactly like the Ka expression. And this is one of the most common problems that students have with these problems, is that they assume that when they solve for Y in this equilibrium, they're actually solving for the hydronium ion concentration. But they're not, and that's why I use Y instead of X to designate that difference. Now, we can do the same kind of thing that we did with the Ka expression. If the Kb is significantly smaller than the initial concentration of the conjugate base, we can make our approximation. So once again, the concentration of the conjugate base minus Y is approximately equal to the concentration of the conjugate base, because Y is so small with respect to it. It's not going to change that number following the rules of significant figures. So if we make that approximation, and again, you need to be careful to follow the guidelines given to you by your instructor in doing that, we get this expression, and again we can solve for Y simply by taking the square root of the Kb value times the initial concentration of the conjugate base. Now, one of the common things again that people forget is that this Y value represents the concentration of hydroxide ion, not the concentration of hydronium ion. So, you need to remember that. And that means that when you solve this problem, you solve for Y, you need to take the POH and then subtract that number from 14. Another thing to think about is if you solve this problem and your solution comes up with a pH value of less than 7, you very likely have made a mistake, and you should go back and double check things and make sure that you did indeed set this Y value for the hydroxide ion concentration. Okay, let's move on to buffers. A buffer is a solution that contains significant concentrations of both the weak acid and its conjugate base. Now, one of the other things that you want to think about with a buffer that we won't treat in this particular screencast is that a buffer can absorb either acid or base from external sources and essentially hold the solution pH relatively constant. And that's one of the reasons why we're so interested in buffers. What we're interested in here, though, is simply identifying a buffer first and then calculating the pH of that buffer. Now, how do we identify a buffer? Well, let's look at some examples. If we have a solution of a weak acid and its conjugate base, that's going to be a buffer. So if we had a solution that contains acetic acid and sodium acetate, and here the acetate ion is the conjugate base of the acetic acid, you notice how the concentrations are fairly close to one another. This would be an excellent example of a buffer. Another example would be if we have a solution that is made by mixing a certain amount of a weak acid with a lesser amount of a strong base. And the reaction between these two would give us a solution that contains significant amounts of both conjugate acid and conjugate base. You could look at this as a titration that has not reached its equivalence point. It's roughly halfway to the equivalence point. So in both of these cases, we would end up with buffer solutions. What is not a buffer is this. If I have a solution that contains hydrochloric acid, which is a strong acid, and sodium chloride, the chloride ion being the conjugate base of the hydrochloric acid, this does not qualify as a buffer, simply because the chloride ion has negligible base strength to begin with. So that is not a buffer. Okay, now how do we determine the pH of a buffer solution? Let's look at this from an equilibrium perspective to start with. Once again, we have our weak acid equilibrium. But unlike a straight weak acid problem, we have both conjugate acid, HA, and conjugate base, A-, in appreciable molarities. We're going to start this out by saying the concentration of the hydronium ion is 0 molar, although again, strictly speaking, that's not true because of the autoionization of water. If we look at it this way, what's going to happen? A small amount of the conjugate acid will hydrolyze to form hydronium ion. And what we end up with then is the concentration of the conjugate acid is slightly diminished and the concentration of the conjugate base is slightly increased. We can plug that into our Ka expression, again knowing the value of the Ka from some external source, and we get this kind of equation. Now, to solve this straight away, we would have to solve a quadratic. But here's one thing to think about. If, in the case of the acid itself in solution, the value of x is very small, in this case the value of x would be even smaller because we already have conjugate base in solution. So what we can say is this: if x is much, much smaller than the concentration of the conjugate acid, then the concentration of conjugate acid minus x is approximately equal to the concentration of conjugate acid. If that's true, then we can also say that x is probably really small with respect to the concentration of conjugate base, since both conjugate acid and conjugate base are roughly the same in magnitude. So that difference is equal to the concentration of the conjugate base, although that should not be a difference, that should be a positive sign there. What we get then is this, and that's very easy to solve. Or we can solve for x simply by multiplying the Ka value times the concentration of conjugate acid divided by the concentration of conjugate base. Since x is equal to the hydronium ion concentration, then that hydronium ion concentration is equal to Ka times concentration of conjugate acid divided by concentration of conjugate base. Now let's simplify this. What we're going to do is start with this equation that we just got from the last slide. Concentration of hydronium ion is equal to Ka times concentration of conjugate acid divided by concentration of conjugate base. Now we know a couple of things. The pH we know is equal to the negative log of the hydronium ion concentration. The pKa is equal to the negative log of Ka. Let's substitute those in. And doing so, we're also going to take the negative log of this ratio of conjugate acid to conjugate base. So what we end up with if we do that is this. pH is equal to pKa minus the log of the concentration of conjugate acid divided by the concentration of conjugate base. Now what I'm going to do with this last term is I'm going to flip the ratio, which is going to change the sign in the logarithm, because if I take the log of an inverse, it's going to be the negative log of the original fraction, or in this case, that would change the negative sign, the minus sign here, to a positive sign, or a plus sign. So if we do that, we end up with this. pH is equal to pKa plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. This is known as the Henderson-Hasselbalch equation and is used extensively for the determination of the pH of buffers. And again, what it does is it assumes the two approximations that we made on the last slide. So, if you identify a solution as a buffer, what you can do is simply plug the values into the Henderson-Hasselbalch equation to determine the pH of the solution.